Hello and good morning friends, welcome to CEC-UGC live lecture. Dear friends, with another lecture on operations research. Today we are going to understand what queuing models is, and for this we have again with us in our studios Dr. Subhash Kakkar. Dr. Kakkar is a dynamic personality because he has immense knowledge, and with the dint of his knowledge he always try to give us something new with excellent examples. So first of all, I would like to welcome our guest Dr. Kakkar. Welcome to the EduSet lecture, sir.
Thank you, Geetika.
And I hope that the way you have delivered your previous sessions, your previous lectures, this lecture is also going to be one of the productive sessions. And sir, through you, we want to know what is queuing model.
Yeah. Thank you, Geetika, and welcome viewers to this series of lectures on operations research. Today we will discuss queuing theory or queuing models. What do we mean by queuing models, and what is the meaning of queuing theory, and how this particular topic is important in our day-to-day life. When we go to any bank or any ATM for withdrawing money, we find queues, and then we stand in the queue. Sometimes we don't stand in the queue, we go to the other counter where we can draw money and where the queue is very small. But again, if we are trying to contact any operator on telephone to get some information regarding the company in which that operator is working, sometimes we are asked to wait, sometimes immediate answer is given to our queries. Again, when we are asked to wait, we are in a queue. And how long we will have to stay in the queue, again that depends upon our experience with that particular operator and that particular company. Suppose we have ATM machines, one installed where we go and to withdraw money, and the queue is very long. Then we will have to wait for a long time. Instead, if there are more than one ATM machines, then maybe we will have to wait for some little time. Again, if there are more and more ATM machines available to withdraw money, then maybe we will go there and take money and come back. We will not have to stay in the queue. And then all it depends upon the service conditions and the arrival rates. What do we mean by arrival rate and the service rate? We will explain just in a minute. Arrival rate is the rate at which the customers come to get serviced at any service center. And at the service center, people are there to cater to our demands, to service us, and they do it at a particular service rate, and that is service rate, the rate at which the customers get satisfied and go back. Now, these two conditions where we talk about arrival rate and the service rate may be constant and may not be constant. The meaning is arrival rate may be fixed and may not be fixed. And what exactly we mean by fixed arrival rate is that, suppose at a ATM machine, we say that 5 customers per minute visit that ATM machine. If this rate 5 customers per minute is constant, then we call it is a fixed rate of arrival. And then this is also called deterministic model. But normally we are not sure that this arrival rate is fixed. Sometimes we find that there is nobody who visits in that particular time slot, and there are certain times when more and more number of customers visit the ATM machine. And similarly, if we approach a cashier in a bank to withdraw some money or to get something done in the bank, then again arrival rate may be fixed and may not be fixed. We say that most of the time this arrival rate is not fixed, it keeps on varying. And similarly, the service rate, the rate at which the cashier attends to us, is again changing. Sometimes it is fixed, sometimes it is changing. When it is fixed, we call it deterministic rate of service. When it is not fixed, we call it changing rate of service. In these two conditions, when it is deterministic and the other one is not deterministic, rates, we call them probabilistic in nature. Now, these probabilistic in nature arrival rates and survey rates follow certain probability distributions. And these distributions are, for arrival, we call it Poisson distribution, which was given by Poisson. And in this particular Poisson distribution, we have average rate of arrival, and similarly exponential rate is for the service rate. At what rate the service facility is available, that is probabilistic in nature, and that distribution is called exponential. Time interval between two arrivals and the time taken by the service center to service the demand of the customers is exponential, and the arrival is called Poisson distribution. Again, now it is very interesting to note that, let us assume the arrival rate is 5 customers per minute at a service center, and the service rate is higher than the arrival rate. Let us assume that this is 6 customers per minute. Customers are arriving at the rate of 5 per minute and they are being getting serviced at the rate of 6 per minute. The point to be noted here is the service rate is higher than the arrival rate. When such is the condition, normally people will think, and normally viewers will think, that there will not be any queue formed, since the service rate is more than the arrival rate. But it is not so. The case is slightly different. Of course, when it is deterministic in nature, exactly 5 customers are arriving per minute and exactly 6 customers are being serviced per minute, then there will not be any queue. But in practice, it is not deterministic. It is probabilistic in nature. These arrival rates and the service rates follow some distributions. When it is probabilistic, then there will be queues formed. When we visit some service center, we will find number of customers waiting in the queue and number of customers getting serviced, even if the service rate is higher than the arrival rate. This particular point and this particular concept, though it is difficult to understand, the viewers must know this before going further. Even if the arrival rate is less than the service rate and the arrival rate and the service rate follow probability distributions, then queues will be formed. Of course, the length of the queue and the number of customers standing in the queue will depend upon the average arrival rate and average service rate. When we visit any service center, we find that the queue is there. We like to wait there, and sometimes we like to don't stand at that particular queue and go somewhere else to get us serviced. Sometimes it so happens there are 3-4 counters available. We stand in one queue. We find that the other queue, the service facility is better than this particular queue where you are standing. You will like to move from this queue to other queue. So it is your choice, and all these conditions have some name. We will discuss all these conditions where we stand in the queue, and jump to some other queue, and we do not like to stand in the queue. All these conditions we are going to discuss, and this probability distribution, how much queue length will be available, and what is the use of this queuing model in our day-to-day life and in solving management problems. And this is also called queuing models or queuing theory or waiting line models. These are all one and the same thing, and the same concept in the theory and the principles are attached to all these similar things. Queuing system. Now, we will discuss about the queuing system. Queuing system, I am forming the queuing system. This particular rectangle is showing the input source from which the customers are being drawn, and then these go to queue where customers are already waiting, and next is queue where people are waiting. In this particular block we have shown 4 customers are waiting there. There can be more than 4 also. One is the input source from which the customers are coming, and this particular block shows the queue, customer waiting in the queue. And next is queue discipline. What sort of discipline is being used by the customers? And then service mechanism. Output is satisfied customer. And this is our queuing system or queuing model. Input source from which the customers are coming, and the queue length where customers are waiting to be serviced. Then we have a service mechanism, and then output means customers leaving the service center after getting satisfied. Customer outside the system and decide to join or not to join the queue. This is input source. And queue discipline is decided before the service mechanism. Service mechanism. Now we will discuss about the service mechanism. First, queue. From the queue, customers are going to get serviced. And then we have a service facility. Okay, in this particular example, there is single channel, single phase, single channel from which the customers are being drawn and going to the service facility. Single channel, number of queues from which the customers are going for getting serviced. And now next is again single channel, means there is only one queue and there are multiple service facilities, So that's why it is called single channel multiple phase. The first one was single channel, single phase. The second one is single channel multiple phase. Multiple means more than one service facility is available, but single channel is single queue is there from which the customers are going. Now, multi-channel and single phase, multi-channel and single phase. Here from queue we see that 2 arrows are coming out, and these 2 queues are there which are leading to the service facilities. There are 2 service facilities. Let us go back. There are 2 service facilities, okay, but each service facility is attached to one queue. So, multi-channel means multiple queues are there, but they are being serviced by only one service facility, okay, only one service station. There is one service station and there are 2 queues. More than one queue means multiple channel and a single phase. Single phase because only one service facility is attached to each queue. Now we will have multi-channel and multi-phase. Now look at this diagram. Okay, customers are being drawn and there are 2 queues shown, and these 2 queues are then attached to 2 service facilities each. It means service facilities are more than one in each case, and even the queues are also more than one. Both queues are more than one, service facility is also more than one, that is why it is called multiple channel, multiple phase. Factors to be observed to characterize the input source. Size, when the customer's arrival is dependent on the number of customers already in the system. Here again I will emphasize the size, which is important. When the customer's arrival is dependent on the number of customers already in the system. When I say in the system, people in the queue and people who are getting serviced, both combined together form the system. Arrival distribution, distribution for arrival rate or time between successive arrivals, inter-arrival time. Again, this is important. This is a factor to be observed to characterize the input source. Arrival control, arrival of customers may be controllable or uncontrollable. Whether these are controllable or uncontrollable, these are the factors which are to be observed to characterize the input source. And again, number of queues, number of channels available. Customer behavior. Now we have to see the customer behavior also. Balking. Customers get discouraged to see the length of the queue, or there is no sufficient space for waiting and decide not to join the queue. Customer goes to the service station, he finds that the queue is there and he gets discouraged because of the fact that queue is very long and he does not like to wait in the queue. The second can be the space is not available where the customer can stand and wait for his turn. Reneging. The customers after waiting in the queue for some time become impatient and may leave the system. This is a typical behavior of the customer. Customer is standing in the queue, then he finds that the service facility is taking more time, then he decides to leave the queue. Then joking is another sort of behavior which the customers depict. Customers who move from one queue to another hoping to receive service more quickly in the second queue. So this is again a typical behavior of the customer, and then they decide to keep moving from one queue to the other, thinking that if we go to the other queue, the time will be less. Queue discipline. Then there is a discipline of the queue also. FCFS, first come, first serve. Very simple to understand. LCFS, last come, first serve. And zero, service in random order. There is no order, random order, pick up the customers and service them. The first one is first come, first serve, second is last come, first serve, and the zero is service in random order. These three disciplines are available in the queues. Classification of queuing systems. And these are classified by 5 parameters and sometimes 6 parameters are also there. A, B, C, D, E, F, and simply we can say that only 5 parameters A, B, C and D and E. 8 stands for arrival process. What is the process being used by the customers when they arrive at a service center? It is denoted by A. Service time distribution is given by B, the second parameter, service time distribution. And C, the number of servers available, means number of service centers available to take care of the customers. D is the system's capacity and E is the queue discipline. So these 5 parameters and sometimes 6 parameters are also there. 6 is the source from which the customers are coming. Now we will discuss these parameters, how important these are. First we discussed A. A is the arrival process. What is the arrival process? Arrival, as we discussed, can be deterministic, can be probabilistic. When it is deterministic, we just simply write D instead of A, showing that there is a fixed rate of arrival of customers in the service center. And the B is service time distribution. Again, if it is fixed, deterministic, then it is D. We write D. If both are deterministic, D oblique D. But in case it is probabilistic, arrival is following some probability distribution, and we call it Markovian probability, and we write M, capital M for arrival, and arrival distribution is Poisson distribution. And similarly, service time distribution, again if it is probabilistic, we write capital M, and that shows Markovian. Markovian is always probabilistic. These two parameters we have already defined now. The third one is the number of servers. If the number of servers available are 1, 2 or 3, we specify 1, 2 or 3. 1 says only one server is there, 2 only 2 servers, and then similarly the number of servers are written. So, MM1 means that arrival rate is Poisson distribution, service rate is exponential, and 1 shows that number of servers available only 1. Systems capacity. Here we specify the system's capacity, whether finite or infinite. We write F for finite and sign of infinity for infinite. And then Q discipline, as we already discussed, first come first serve, FCFS, last come first serve, LCFS, and third is 0, service in random order. We write SIRO, FCFS like this in the E position. So, this describes the queuing system. A typical example is shown here, MM1 and the sign infinity and FCFS. This is a queuing system. This means the arrival rate is following Poisson distribution, service rate is following exponential distribution. That is why M and M are written. There is only one server which is written as 1, infinity, infinite source from which the customers are coming, and the Q discipline is FCFS, first come first serve. So, this defines the queuing system. Some terms and symbols which are used in queuing models are now being explained. The first one, small n, number of customers in the system waiting and in service. Pn, Pn is the probability of n customers in the system at any point of time. Pn is the probability of n customers in the system at any time. Lambda is mean arrival rate, and it is regarding Poisson distribution. Average arrival rate is shown by the symbol lambda. Mu is mean service rate, the rate at which the customers are being serviced is denoted by mu, and the rho is nothing but lambda by mu, and this is known as traffic intensity, the expected fraction of time in which servers are busy. This is shown by lambda, and it is the formula for rho is lambda by mu, and rho is called traffic intensity. S, number of service channels. LS, mean number of customers in the system waiting and in service. Here we are talking about the system itself. There is a queue and there is a service center. People standing in the queue and people getting served together is called LS, which is the mean number of customers in the system. Here it is system. And then WS, mean waiting time of a customer in the system, queue time plus service time. People have to stay in the queue and there is time required for getting serviced. The total time is called WS, okay, waiting time in the system. L, mean number of customers in the queue, mean queue length. And WQ, waiting time of a customer in the queue. And then we have other terms like L is greater than 0, mean length of non-empty queue. When L means number of customers are not 0, more than 0 means 1 or more, then mean length of the non-empty queue. And similarly, W is greater than 0, which means mean waiting time, When it is 0, customer will not have to wait. If it is more than 0, only then the customer will have to wait. That is why we call it W greater than 0, mean waiting time. Now, we will discuss some of the formula. LS, number of customers waiting in the queue, is equal to lambda into WS, where W is the waiting time in the system, waiting in the queue as well as waiting in the service center. LQ is lambda into WQ, lambda into WQ. Lambda is average arrival rate, W is the waiting time in the queue, L is the number of customers waiting in the queue. WS is the WQ plus 1 by lambda plus 1 by mu, and this gives the waiting time in the system. Distributions for arrival rate and service rate. As we discussed, Poisson distribution is a distribution for arrival rate, and probability of any number of customers waiting in the queue are given by Px equal to e raised to power minus lambda and lambda raised to power x divided by x factorial. And similarly, exponential distribution for service rate Px is given by mu e raised to power minus mu x. And this needs some explanation. Lambda is the average arrival rate. Now, suppose we stand outside the gate of our institute and we keep on noting the number of cars which pass through that gate in 1 minute, and if we take the average value, and that average value is given by lambda. Again, let us assume in our hypothetical case, and this average is 10 cars per hour. Now, the probability of knowing 5 cars passing through that gate, how we are going to get it, and the formula for that is the Poisson distribution. Here we have discussed lambda is 10, but the x is 5. So, formula will change e raised to power minus 10, 10 raised to power 5 divided by 5 factorial, and this will give us the probability of just 5 cars passing through that particular gate, where the average passing rate is 10 cars per hour. Similarly, is the explanation for exponential distribution. The formula for that is Px equal to mu into e raised to power mu x. Then there are certain formula one has to remember, though one can calculate from 1 or 2 formulas, other formula can be made. And then Ls is equal to lambda by mu minus lambda, where lambda is the average arrival rate, mu is the average service rate, and Ls is the queue length in the system. or this can be also written as rho divided by 1 minus rho, because the first formula, if we divide numerator and denominator by mu, it will become lambda by mu, 1 minus lambda by mu, and lambda by mu is known as rho, which is a traffic intensity. So, this formula can be changed and it can be formed in the form of traffic intensity, which is shown by rho. Expected number of customers in the queue. Earlier we have discussed LS, number of customers in the system. Now we are discussing LQ, means number of customers standing in the queue, which is given by lambda square divided by mu within brackets mu minus lambda. Here we are discussing the cases where mu is greater than lambda. Service rate is greater than the arrival rate, and to this particular point we have had already a great discussion. Though the service rate is more than the arrival rate, we will find the queues being formed because they are probabilistic in nature. One follows the Poisson distribution, the other follows the exponential distribution. Average waiting time in the system Ws is given by 1 divided by mu minus lambda. Average waiting time in the queue Wq, and the formula for that is lambda divided by mu within brackets mu minus lambda. Expected length of non-empty queue, mu divided by mu minus lambda is a formula for expected length of non-empty queue. And the probability that there are n customers in the system, Pn is equal to lambda by mu raised to power n into P naught. And then again probability that there is nobody in the queue, P0, is given by 1 minus lambda divided by mu. So, these are the formula we have to remember while considering the problems of queuing theory, queuing model. Probability that there is at least one customer in the queue is given by Pb 1 minus P0. Traffic intensity we have already discussed is given by rho, which is equal to lambda by mu. Now, we will discuss some examples so that we get conversant with this queuing models, queuing theory or waiting line problems. A repairman is to be hired to repair machine which break down at an average rate of 3 per hour. The breakdowns follow Poisson distribution. Non-productive time of a machine is considered to cost rupees 10 per hour. 2 repairmen have been interviewed. One is slow but cheap, while the other is fast but expensive. The slow repairman charges rupees 5 per hour and he services breakdown machines at the rate of 4 per hour. The fast repairman demands rupees 7 per hour and he services at an average rate of 6 per hour. Which repairman should be hired? This is a question. Let us go back to the previous slide. Here, breakdowns at an average rate of 3 per hour. So, 3 per hour is our arrival rate. Machines to be attended for breakdowns on an average are coming at 3 per hour. And 2 repairmen are available. One is slow and cheap, other is fast but expensive. And we have to decide which one to hire. And we know that cost of inoperative machine also. Let us see how to calculate, how to solve this problem. Solution is average breakdown of machines 3 per hour. The value of lambda, average arrival rate is 3 per hour. And the cost of idle time per hour is rupees 10. And this is according to the given data. Now, let us assume we have a slow repairman on the job which has a servicing rate of 4 per hour. So, we will write mu is equal to 4 per hour. Mu is the service rate. Hourly charges are rupees 5. And average number of machines in the system, LS, means getting repaired as well as waiting in the queue, is given by lambda divided by mu minus lambda, which is equal to 3 divided by 4 minus 3 is equal to 3 machines. Let us concentrate on this particular point of the solution. Average number of machines in the system waiting for repairs. Machine is broken down. Repairman is repairing one of the machines and other machines are waiting. The total number of machines which are not operative is the number of machines in the system, LS. And the formula for LS, which includes waiting time as well as service time, is lambda divided by mu minus lambda. Lambda is the arrival rate, average arrival rate, mu is the average service rate. So, we get 3 machines at any point of time. As per this formula, 3 machines will be inoperative. Therefore, machine hours lost in 8-hour shift. Let us assume for the 8-hour shift all the calculations. Per hour there are 3 machines which are out of order. For 8-hour shift there will be 3 into 8, 24 machine hours will be lost. 24 machine hours will be lost. Let us go back to the original. So, we say that 3 machines are out of order at every hour. So, 3 machine hours are lost and out of 8 hours, 24 machine hours will be lost. Total cost, higher charges of repairman plus cost of idle machines. Higher charges for 8-hour shift and then machine downtime loss. 5 into 8 plus 24 into 10 is equal to rupees 280. 24 machine hours are lost and the machine hour loss is rupees 10 per hour. 24 into 10 and 8-hour shift, the repairman is charging 5 rupees per hour. So, total is 280 is the amount which we will have to spend when we hire a slow repairman. Now, let us see what happens when we hire a fast repairman. Fast repairman servicing rate is 6 per hour. So, in this case mu is 6 per hour, hourly charges are rupees 7. Average number of machines in the system, LS, again the same formula, lambda divided by mu minus lambda, which is equal to 3 divided by 6 minus 3, 1 machine only. In this case, 1 machine is waiting in the system. Therefore, machine hours lost in the 8-hour shift, 1 into 8 machine hours are lost in 8-hour shift. Total cost now, higher charges plus higher charges of the repairman plus cost of idle machines, as we did in the case of a slow repairman. In this case, 7 into 8 plus 10 into 8 is rupees 136. So, against 240 rupees, we are to spend only 136 if we hire a fast repairman. Therefore, the answer is it is advisable to hire the fast repairman as the charges are less in this case. So, these kind of problems can be solved using queuing theory and queuing models. We will have more examples also, we will discuss those examples also, so that our viewers get conversant with the principles of queuing theory. The second example, in a railway marshalling yard, goods train arrive at a rate 30 trains per day. This is the arrival rate. Assuming that the inter-arrival time follows an exponential distribution and the service time, the time to be taken to hump a train distribution is also exponential with an average of 36 minutes. Calculate the following: the mean queue size, the probability that queue size exceeds 10. So, we will see how to solve this problem. If the input trains increase to an average of 33 per day, then what will be the change in 1 means first answer and the second answer. There are 3 questions which are to be answered. Solution is now from the data of the problem we have lambda is 30 divided by 60 into 24 because on daily basis. So, 1 by 48 is the lambda and similarly mu is 1 by 36 per minute. If we go back to the statement of the problem, it takes average of 36 minutes. So, with 36 minutes, we have calculated the mu value 1 by 36, 1 by 36 trains per minute, and similarly lambda is also 1 by 48 per minute. Trains are coming at the rate of 1 by 48 per minute. These two values are very important, the value of lambda and the value of mu. In this particular example, we have calculated lambda as 148 and mu as 1 by 36. The traffic intensity is rho. Rho is given by lambda divided by mu, which is 36 divided by 48. The answer is 0.75. So, traffic intensity is 0.75. This means 75% of the time the yard will be busy. Thus, we have now we can calculate easily the LS, queue length of the system is rho divided by 1 minus rho, 0.75 divided by 1 minus 0.75, which is equal to 3 trains. 3 trains are there in the system. And next is the probability, queue size. Now, we want to get an answer, queue size greater than 10, probability of having trains greater than 10, which is equal to lambda by mu raised to power 10. Because this is a formula to be used, 0.75 raised to power 10 is 0.06. So, 6% is the desired probability. Now, when the input increases, arrival rate increases to 33 trains per day. We have now lambda changed. Lambda is now 33 divided by 60 into 24. 24 number of hours in a day and 60 minutes, and this is based on per minute basis. 1 by 43 are coming per minute and mu already calculated is equal to 1 by 36. And the rho traffic intensity is lambda by mu, which is equal to 36 by 43, and this is 0.83. Consequently, our two answers will now change. The first LS, the formula what we used earlier, the same formula will be used, which is that rho divided by 1 minus rho, where rho is the traffic intensity. Again, it is equal to 0.83 divided by 1 minus 0.83, answer is 4.83, or 5 trains in the system waiting and getting serviced. Probability of queue size greater than 10, again the same formula, this probability raised to power 10. So, answer is 0.2 approximately, so 20% in this case. So, this is the way to solve our problems. Formulae we are going to use, which we have already discussed and explained, and to our desired questions and the queries we use this formula and get answers. We will have one or two more examples so that our viewers get acquainted with the queuing model and queuing theory and waiting line problems. Another example, an airline has one reservation clerk on duty at a time. He handles information about flight schedules and make reservations. All calls to the airline are answered by an operator. If a caller requests information or reservation, then the operator transfers the call to the reservation clerk. If the clerk is busy, then operator asks the caller to wait. When the clerk becomes free, the operator transfers to him the call of the person who has been waiting for the longest duration. Assume that arrivals and service follow Poisson and exponential distributions respectively. Call arrive at the rate of 10 per hour and the reservation clerk can service a call in 4 minutes on the average. What is the average number of calls waiting to be connected to the reservation clerk? What is the average time a caller must wait before reaching the reservation clerk? What is the average time for a caller to complete a call? That is waiting time plus service time. These three queries are to be answered. Now, we have discussed or thoroughly understood the problem. How to answer these questions, we will see. Solution is like this. From the given data, we know that lambda is 10 by 60 per minute. These are the number of customers giving the calls. Mu is 1 by 4 per minute. Let us go to the main problem. Here, one reservation clerk, server is one, on duty, he handles information about flight schedules. All calls to the airline are answered by an operator. If a caller requests information or reservation, the operator transfers the call to the reservation clerk. If the clerk is busy, then operator asks the caller to wait. When the clerk becomes free, the operator transfers to him the call of the person who has been waiting for the longest duration. This shows the discipline of the queue, first come, first serve. Assume that arrivals and services follow Poisson and exponential distributions respectively. Calls arrive at the rate of 10 per hour, arrival rate is 10 per hour, and reservation clerk can service a call in 4 minutes. So, this gives the service rate also. From this, we will have the answer. Per minute, arrival rate is 10 by 60 per minute and the service rate is 1 by 4 per minute, because 4 minutes are required to service one of the caller. LQ, average number of calls waiting. Queue length, the formula for this we have already discussed, lambda square divided by mu minus lambda, which is 10 by 60 whole square divided by 1 by 4. And which is the answer is 1.33. And the waiting time in the queue, WQ average time a caller must wait is lambda divided by mu within the brackets mu minus lambda 10 by 60, 1 by 4 and then 1 by 4 minus 10 by 60, because it is mu minus lambda. The answer is 8 minutes. So, answer we get is waiting time in the queue is 8 minutes. And the length of the queue is 1.33 customers waiting, and the given data was arrival rate was 10 by 60 means 1 by 6 per minute, and the service rate mu was 1 by 4 per minute. So, WS waiting time in the system, average time for a caller to complete a call is 1 divided by mu minus lambda. Is again equal to 1 divided by 1 by 4 minus 10 by 60 is equal to 12 minutes. So, this completes the answer to this our question. So, I am doing some of the examples for the help of viewers so that they get conversant with the queuing models and the queuing theory. We will discuss one more example. This is again an example of queuing theory. Arrivals at a telephone booth are considered to be Poisson with an average time of 10 minutes between one arrival and the next. This again gives a arrival rate. The length of a phone call assumed to be distributed exponential with the mean 3 minutes. This gives a service rate. The first one gives us a arrival rate, the second statement gives us the service rate. Now, questions to be answered are, what is the probability that a person arriving at the booth will have to wait? What is the average length of the queues that form from time to time. And the third one is, department will install a second booth when convinced that an arrival would expect waiting of at least 3 minutes for the phone. By how much must the flow of arrivals be increased in order to justify a second booth? Just reading this problem, it looks difficult one, but now we know the theory of queuing models and we know the formula to be used, and we will get answers very quickly to these queries, to these three questions. The solution is like this. From the data of the problem, we have lambda, which is arrival rate, which is 1 by 10 person per minute. Let us go to the problem. Average time of 10 minutes between one arrival and the next arrival. It means every 10 minutes we are getting one customer. That is why 1 by 10 person per minute is the arrival rate. Similarly, 3 minutes is the call time. That is why the service facility is busy for 1 by 3 person per minute. So, mu in this case is 1 by 3 persons per minute, because service is being rendered at the rate of 1 by 3 persons are getting satisfied per minute. Now, we want to know the probability of W greater than 0, which is equal to 1 minus P0. We want to find out the probability of getting Qs. Here we will subtract probability of empty Q from 1, which is equal to lambda by mu, which is equal to 1 by 10 again divided by 1 by 3. 1 by 10 is the value for lambda, 1 by 3 is the value for mu. The answer is now 3 by 10, rather 0.3. So, the first answer we get is 3 by 10. Next is L greater than 0. Non-empty Qs means Q is there. We want to know that probability. Then the answer where the L is greater than 0 is mu divided by mu minus lambda, which is equal to 1 by 3 divided by 1 by 3 minus 1 by 10. After simplification, the answer is 1.43. And similarly, WQ, waiting time in the queue, is now lambda divided by mu within brackets mu minus lambda. Hence, WQ, waiting time in the queue, is 3, and mu minus, now mu is equal to 1 by 3 and lambda is equal to lambda dash. Say for example, now we want to know the new lambda, new arrival rate, when the company will decide to have one more server, second booth, and we want to know the new arrival rate, which is more than the earlier arrival rate, and we want to know to what extent the arrival rate changes, increases, so that the company will have one more extra booth. So, the formula to be used is now 3 we already have know is equal to lambda dash divided by 1 by 3 within brackets 1 by 3 minus lambda dash. The answer is now the new lambda, the value of new lambda is 0.16. Earlier lambda was 1 by 10. 1 by 10 is nothing but 0.1. Now, the lambda means arrival rate is increased from 0.1 to 0.16 per minute. Therefore, the change in arrival rate which we are looking for is 0.16 minus 0.10, which is equal to 0.06. If this is the increase in the arrival rate, then this will prompt the company to have one more booth. So, different types of problems, different types of questions we are discussing, so that we get conversant with the queuing models and the queuing theory. We will discuss one or two more examples. Suppose, another example, suppose that all car owners fill up when their tanks are exactly half full. there is a petrol pump where people take their cars to get the CNG or gas or petrol filled up in their petrol tanks. At the present time, here the condition is when they find that their tank is half full, they go to the petrol pump and get it filled up. At the present time, an average of 7.5 customers per hour arrived at a single pump gas station. Now, the third statement given by this problem is takes an average of 4 minutes to service a car. Assume that inter-arrival and service times are both exponential. For the present situation, compute L and W. Suppose that a gas shortage occurs and panic buying takes place. To model the phenomena, suppose that all car owners now purchase gas when their tanks are exactly 3/4 full. So, instead of half full, now when the condition is only when they have used only quarter of the tank, they want to get it full. Since each car owner is now putting less gas into the tank during each visit to the station, we assume that the average service time has been reduced to 3 and 1/3 minutes. How has panic buying affected L and W, queue length and the waiting time? This is a very practical question and we will find an answer to this question also. Solution. We have in this case the model is MM1 GD infinity with lambda 7.5, cars per hour and mu equal to 15 cars per hour, and the same principle, same theory and same formula can be used to get an answer to this particular question. And so let us discuss only one formula where the length we want to calculate. 5/6 divided by 1 minus 5/6 is equal to 5 cars, and the waiting time W is L by lambda 5/15 1/3 hours, which is equal to 20 minutes. If we use this formula, we will get answers to our queries, answer to our questions. We have discussed 5 formula so that viewers can get conversant with the principles of queuing models, waiting line systems. I hope I am able to explain the concepts of queuing theory. Now the viewers can make use of this theory to get a reply to their different queries.
With this note, thank you sir, thank you so very much, because we have no time left over here and we would like to tell you all that Dr. Kakkad would be again with us tomorrow and we would be discussing new topic. Thank you sir, thank you very much.
Thank you.